Okay, so I have just shared this first. Let not share this. Just a minute, I'll post the previous things of the morning. So we'll start. Okay, so we'll finish with inshallah unit 2 today, 23rd class. That's the last topic and the simplest one that's left off. So in the previous class, what we have seen, Zaid, do you remember? In the morning class, in the evening, yesterday's evening class. So starting with our new topic. Okay, so it's 2.3 to 2.3, and the topic is that transforming. What to transform? Transforming. What to transform? It's the data to achieve linearity. To achieve linearity. Okay. So we have seen that there are general plots which are likewise not straight. They are going like this. Some wise they are going like this also, or you may say maybe like this. Okay, or they were going in the form of the curve, likewise like this. It can be a data which is having like this also. Okay, so there must be some data with different patterns. So from these patterns, as they are not linear, they are having a curve. Okay, so first of all, what we'll do, we'll look onto various curves of various functions, so you'll understand what we are doing. Okay, so graph of logarithmic function log. See, how's the graph of log? See here. You can see it here. Okay, this is the graph of log. Okay, there we here you also you can see this is a graph of log to the base 3. This then we can see graph of e power x, e raised to x. Okay, you can see here e raised to x. This is the perfect graph of e raised to x. Okay, so then we have the graph of some power raised to x, that's a raised to x. It is also like this only. See, 2 raised to x. So here is a 2 raised to x graph. Okay. So as A will increase, the graph will contract towards the y-axis, tending to. So
Mm-hmm.
this was the thing that I wanted to show you the graph. What we will generally do, that if the graph has a logarithmic curve, then we'll apply log onto the explanatory variable, explanatory
Mm-hmm.
explanatory variable. Okay, so we'll see in this. Just read it. I'll drink some water. Just read this.
All right.
Okay, so what he has he written that in section 3.2 we learn how to analyze relationship between two quantitative variables that showed a linear pattern. By when bivariate data show a curved relationship, we must develop a new technique for finding an appropriate model. So this section describes several simple transformation of data that can straighten the non-linear pattern. So if we want to straighten a non-linear pattern into a linear pattern, we have some techniques for
Mm-hmm.
for changing a non-linear changing a non-linear pattern into a linear pattern. There are some techniques. What are those techniques generally? Okay, so we are going to see those techniques in this chapter. So yeah, see, the Gapminder website provides loads of data on the health and well-being of the world's inhabitants. Show a scatter plot of data from the Gapminder. The individuals are all the world nation for which data were available in 2015. The explanatory variable income per person is a measure how rich a country is. The response variable is life expectancy at birth. Okay, so this is the data. This is the data you can look at. Okay, so just see the data. I'll attend one call. Slavic. Thanks for waiting. That was an important call. Okay, so see, this is some
Oh,
data that he has
yeah.
plotted here. For green is for America,
Mm-hmm.
yellow, light yellow is for Europe and Russia, reddish or orange is for Asia and Pacific, and the blue is for Africa. So he has plotted what he has plotted: income per person and life expectancy in years. Okay, so how much is the life
Mm-hmm.
expectancy? So what you can see is this plot linear scatter plot. No, it is not linear. It is having a curve. Yes or no?
Uh-huh. Yeah.
Yes, it is having a curve. So what we'll generally do that we will see what methods are there. Okay, I'll take this graph on paper board. So see, you can see here that it is having a what pattern? Is it linear? Is it linear, Zaid?
No, it is not.
No. So we need to do something that it becomes linear. We achieve linearity. Okay, so what we'll do,
Mhm.
so what he has done, that we expect people in the richer country to live longer because they have better access to the medical care, and typically lead healthier lives. Typically lives healthier lives. Okay, the overall pattern of the scatter plot, does show this, but the relationship is not linear. Life expectancy rises very quickly as income per person increases and then levels off. So as the income per person increases, expectancy of lives also increases. People in very rich countries such as United States live no longer than people in the poor but not extremely poor nations. In some less wealthy countries, people live longer than in the United States. So somewhere it is like that in poor countries in like see Asia and Pacific, your people live longer compared to the Americas. Okay, they are a moderate, you can say moderately rich countries. Yes or no? In moderately rich,
Mhm.
correct. But America is extremely rich in their economy, extremely rich, and people also there are extremely rich there. So, but there is a difference between very poor, which is Africa. See, Africa has very small dots here. Okay, so there is a big comparison between here and also in moderately rich countries and all, but there is no comparison between what you can say the things in Africa and here. So therefore, it is non-linear. Okay, four African nations are
Mhm.
outliers. He is comparing that four African nations. Where are they? I think so. Here he is telling here African countries. Okay, see. Okay, here. He has given. Okay. So outliers, their life expectancy are much smaller than would be expected based on the income per person. So what the scatter plot is shows a curved pattern. Here I am reading from now. The scatter plot shows a curved pattern. We can straighten things out using logarithms. Plot the logarithm of income per person against life expectancy for these countries. So what we have taken, we can straighten lines out using logarithms. So what we will do for each data point. For example, I am having the years, what you guys, life expectancy. Okay, life, and here is the income. So what I'll do for is suppose it is 1,000, then it is 80,000. Okay. So what I'll do, I'll apply log on income. I'll apply log on income. So I'll see log of 1,000 for suppose it is 2.33. For I'm just taking it, not assuring that it is 2.33, just supposing it is 10.11. So I'll apply log and plot this in with this. This will be our x and this will be our y. Did you got that, Zaid?
Mhm.
Yes. So when we'll plot this, you see you can look the alert data. Yes or no? Is that linearity?
Yeah.
Yeah, it has become a straight line. Okay, that's the thing. Applying a function such as logarithmic or square root to the quantity data. What we are applying, either you can do logarithmic. If it is very big difference, so you have to apply logarithmic. If there is a small difference, you can also apply square root. Square root. Square root on the
Mhm.
data. Okay, that's the
Yep.
thing. Square root to the quantitative variable in was called transforming the data. When we apply it on the quantitative variable, it's called as we are transforming the data. This is very easy topic as things are. So transforming data amounts to changing the scale of the measurement that will use when the data were collected. In if we discuss linear transformation such as converting temperature into degrees Fahrenheit, degrees, converting distances into mile and kilometers. However, linear transformation cannot strain it. We have studied that if we change the units, it doesn't changes, but cubing and all, it can we can think of it. Okay, so the logarithmic function applied in the income and life example is a non-linear function. We'll return to the transformation involving logarithmic later. Now he's transforming data using power and roots. We can also transform the data if see it was in an increasing state here, so we have taken log which has reduced the things and bring it. I'll take that graph, also the reduced one. See, as it was like this previously,
Mhm.
now it has become like this. So it was an increasing pattern. So what he has done, reduce the things. Okay, for suppose it is in this pattern. For suppose it is in this pattern. Okay, this pattern. So what we'll do, we have to take
Yeah.
upside. Am I audible, Jay?
Yeah, you're audible. I can hear you.
Yes.
I'm
So
just listening.
okay, okay. So if it is in this pattern, okay. So if it is in this pattern, so what we can do, cube this exploratory variable. So it will be strained. See, we'll see one example here. Downside. Now he's transforming the data by using powers and roots. Okay. So this was the thing. When you visit a pizza, so the area of that is measured. Okay. Pendulum and all. So we can also square and take the square roots of the what you may say the exploratory variable. He's telling us that. Just read this. Come on.
All right. Yeah, read it.
So what he's telling that when you visit a pizza parlor, you order a pizza by its diameter, says 10 inches, 12 inches, 14. But the amount you got to eat depends on the area of the pizza. The area of a circle is 5 times the square of the radius. So the area of the round pizza with diameter x is it is
Mm-hmm.
5 by 4 x squared. This is power model of the form y equals to ax raised to p with a equals to pi by 4 and p equals to 2. So when we are dealing with things of the same general form, whether circles or fish or people, we expect area to go up with the square of the dimensions, such as diameter of height. Volume should go up with the cube of the linear dimension. That is, geometry tells us, and that's all the thing that we have read. That's simple. So we'll move on to the next thing. So see here, he has given one data. Here he has given one data here. So what he's trying to explain us is that what he's trying to explain us, he has given here the data, okay, for the length and the weight. Correct? What data it is? Imagine that you have been put in charge of organizing a fishing tournament in which prizes will be given for the heaviest Atlantic ocean rockfish caught. So it is the length of the fish and the weight of the fish that is being caught. Okay. Both the things depend upon the length and the weight. So what we have done, it was non-linear. So I've told you when the data is going in this sense. When the data is going in,
That sense.
yeah, wait a minute, it is connected. When the data is going in this sense, okay, so we
Mm-hmm.
generally cube the exploratory variable or take square. You can do anything. You can try both these things and see when linearity comes. So he has seen that when he has taken the cube of the length, he has cubed the data, taken the power as cube of the data. So it has become linear. Yes or no, it has become linear or not?
Yeah, it becomes linear.
That's the thing, how to transform the data. So we have calculated, see, the all the things, regression analysis using that, and he has asked some questions. Come on, read this whole thing and give me answer of the questions. Come on.
Okay. All right. Then. The least square regression line is
Yes,
4.06 plus 0.0146740
correct, correct.
times the length.
Yes, correct. Yes, that's good. Right. Correct. See, length cube, because we have taken the cube of the length. Correct, na?
Oh, yeah, length cubed.
Length cube. Okay. See, so that's simple. Okay, so we'll go further. Come on, come on, give me the answer of this also first.
Mm. Mm.
Come on, give me the answer.
I'm reading it. Don't worry.
Again, it's the length. It shows the relationship between the length and the cube root of weight. Okay, he has taken the
Mm.
cube root of weight now here in this problem. He has given listed here. Okay, so for Atlantic Ocean of Physics, the computer output from a linear regression analysis, y equals to cube root of weight versus x equals to length.
Mm.
X equals, see now, here, he has taken cube root of weight versus length. Okay, so what will be the equation? It will be the minus 0.2204 plus 0.
Mm.
It will be 0.246616 into length. Yes or no? No.
Yeah.
It into, no, wait.
Really?
Into length it will be, no? Yes, into length. Yes or no?
Yeah. Yeah. Be length, not weight.
Yes,
Weight is
and
the Y.
correct. Yes, and this will be weight will be always x, the predictory variable,
Mm.
the
Yeah.
explanatory variable.
That's is always the Y is always influenced by that.
Correct, correct. That's right. Now we are doing some calculation based on the bit. So this was the output of it. It's easy. Okay.
Mm.
So C has given some points here. I've shown
Yeah.
you that if it is showing likewise like this relationship, like this, we have to cube. Okay, we have to take the cube or the square. You can take any power. Cube is much better. And if it's showing like this relationship, you can take the log to bring it to linearity. Okay.
Mhm.
So that is the value of explanatory variable x to p power and plot it is x raised to p, or take the p value of the response variable to the plot the point. That's the root. P through transforming with logarithmic power models. So this is also a thing that what we can do. Take the logarithms on board the equation using the properties logarithm we get. Likewise, also we can do the equation. That's simple. See what he has done. First, we have standard log of length he has taken. Then same we have plotted the what you will say residual least square regression line with it. Yes or no, Zaid, in this example?
Yeah. Exactly.
You can see this example as your homework. Alhamdulillah, we have finished
Mm-hmm.
with the unit, you can say. That's all for your revision purpose. Okay, then exponential form, how to transform it. These are the ways you can read it as your homework. These are simple. How to transform that things. Just you have to do the cube of that column and then plot it. See here. One more example. Here, the data, it was see, it is going non-linear type. What we'll do, cube it. So see what he has done. He has taken log of transistors here. Log of, he has taken the transformation of the explanatory variable. Here, predictory, yeah, response variable. See how the data is transformed. Yes or no, you can take any variable and transform it. Not a problem. Okay. So today it will be half an hour only class as we have finished all the things.
Uh,
Okay. So you can practice
yeah.
for your tomorrow's test. Is it clear? Any
Yeah.
doubt? Okay.
Yeah. It's clear. It's clear. Yeah. I just disconnected for a moment.
So this is a summary for 3.3. We'll revise once more these things tomorrow. And our test, I will,
Yeah.
today is Friday, correct? Yeah.
Yeah.
Will you join at 4:30 or
Yeah.
5 p.m.?
I need my sleep.
Is it possible?
Uh. Yeah. No.
5 p.m. not possible?
No.
No, okay, no problem. So I'll forward you the test tomorrow. We'll take a class tomorrow at the same time, 6:30 a.m. Then you can do the test in the
Mm-hmm.
afternoon when you don't have school, right? On Saturdays?
Yeah, that's cool.
Yes, no school. So I'll transfer you the test. I'll take the class in the morning, 6:30 a.m. Then transfer you the test. You can. It will be on the first chapter. Correct? Is it clear?
Mm-hmm.
Tomorrow onwards,
Yeah,
we'll
it's clear.
revise this last topic in the tomorrow's class, and we'll have two classes on. Is it clear? Two classes on Saturday. One
Yeah.
I'll one I'll take at 6:30 a.m. Then I'll forward you the test. You do that test between 7:30 a.m. to 3:30 p.m. anytime. Then we'll have a class on 3:30 p.m. Is it clear for tomorrow?
Yep, that's clear.
Okay. So this was wrap up for chapter 3. Okay. So you practice sums. We'll see the chapter 3 performance. Assalamu alaikum.
Oh, wait. We're leaving so soon?
Yes. Yes.
We're leaving now? I think it's way too early.
Very early.
Yeah, very early.
So
Only
shall we do
34
sums?
minutes.
Shall we do sums?
Yeah, yeah.
Okay, we'll do some sums. Come on, shall we? We'll do some sums. Okay, come on. Do this one.
Yeah, this is not a linear regression line.
This is,
A curve.
you're doing this, right?
Yeah.
Yeah, do it.
What is the question then?
You have read the question?
Yeah.
You have the text, right? You can open the text in your mobile, or you if you have the hard copy, so you can open it.
I don't have the hard copy right now.
You don't have the hard copy right now.
No.
No, so okay. So we'll do a smaller question. It's more visible. Okay, here is the smaller one. Come on, you can answer this. Come on.
Exponential. Probably so we can graph the amount of success it has gained. Huh.
Guess what is telling? Here is a scatter plot of fraction base E logarithmic of the number of transistors on a computer chip versus
Yeah,
the
I think it's
years.
better for it to be an exponential graph so it can show more growth.
Correct, correct. So what's the solution? We'll see here. See the scatter plot of the Ln transistor versus years since 1970 has a fairly linear pattern, so an exponential model seems reasonable here. So it will be an exponential model. So we'll apply exponential there. Okay,
Hmm?
means we'll apply ln to y, ln to the response response variable. Okay, so next question was the V1. Here is some computer output with the linear regression analysis of a transform data. Give the equation. Come on, you can give the equation of the least square regression line. Be sure to define any
Plus 7.2272 plus 0.3542 times year since 1970.
variable. Use your model from part B to predict the number of transistors on an Intel computer in 2022. Okay, so it was
Mm,
C. Yeah,
50.
yeah, yes.
You
That's
multiply that, you get 67,622,053 point. Okay, 67,622,000.
correct.
Is it billion? Oh, it's okay. So 67,622,053,360.
Correct, correct.
There we go.
Here's the linear regression graph also. We can look at one more example here. Come on, look at this. Read this.
exponential graph.
Yes. What we'll do, we'll take the log of the exploratory variable, explanatory variable. See here what he has said. I'll answer the question. All these
It's a
three.
linear graph.
It will be a linear when we'll apply log on it.
Yeah. Okay. Yeah. I guess so. Sure.
Yes. Based on the output, explain why it would be reasonable to use power model to describe the relationship between weight and length of the Atlantic rockfish. So as it is a power
Mm-hmm.
model, why it is a power model? Because it is not linear. So we have applied ln on the x. Okay, give equation of least square regression line. Be sure to define any variables you use. So it will be minus the it will be what you will say. We have taken log on both weight as well as length. So log of weight equals to log of weight hat equals to minus 1.899 plus 3.0492 into x. Correct? Right?
Mm-hmm.
Correct. Because we have applied both log on both the exploratory as well as the that thing also. Okay. So and the third question is, suppose a contestant in the fishing tournament catches an Atlantic Ocean rockfish with 36 centimeter long. Use the model from part B to predict the fish weight. So you can see 36 we'll use and we'll predict the fish weight. See is the end of the
Mm-hmm.
question. Is it clear, Zaid, how to calculate and all?
Yeah, that's clear.
So we'll end it today here only. Is it okay?
Mm. Okay. Got it.
Come on. We'll have a test tomorrow. Thank you. Assalamu alaikum. Allah Hafiz.
Walaikum salam. Allah Hafiz.